to our online workshop. I'm Katie Jovanovska, Marketing Program Manager at Kumo AI, and I will be your host today. We are thrilled to have Jure Leskovec, Kumo AI co-founder and professor at Stanford University, along with Ben Berger, data scientist at Kumo AI, here with us for this exciting workshop on predictive modeling without feature engineering. It's important to mention that during this session, you will learn new concepts in relational deep learning and how it leverages graph neural network, also how to solve predictive modeling problems using RDL, and how it compares to traditional ML methods on benchmarks like RealBench. Also, you will be able to learn how to achieve the same results in less time using the Kumo SDK with added evaluation and explainability features. Before we begin, please remember to use the Q&A section to ask any question throughout the session. At the end, we will dedicate time to answer the most relevant question in the order they are received. I hope now we are ready to start. Let's dive in. And now I'd like to invite Jure Leskovec, our Kumo AI co-founder, to begin this workshop. Jure, over to you.
Yeah, thank you so much, Katie. Nice to meet you all. Very excited to talk to you today. Thanks for attending in all kinds of different time zones and making time in the morning, evening, or the afternoon. There's always a good time to learn more about machine learning and AI, I guess is the conclusion. So I'll talk to you today about some very exciting work, how to bring the true power of AI to relational data, to structured, semi-structured data, to be able to learn from it automatically and build great models that truly move the business metrics. So when I talk about structured data, I mean data stored in tables, and these tables are interlinked with primary foreign key relations. This is the most valuable, the most useful, the most treasured data that organizations, companies have. This is not public data found on the internet, but this is really kind of the blueprint, the DNA of every single business, and it's what makes that business unique, because it's kind of a record of how a business operates, how do different entities in that business relate to each other, how they evolve over time, and so on. So, what are some examples? In commerce, a natural example is in terms of having customers, transactions, and products. So customers buying products through transactions and these tables linking each other. In finance, you have accounts and transactions and credit cards and clients and things like that. And of course, every of these tables has many different columns. And then, in, let's say, media, social media, and just generally, you can also think of data in terms of, again, tables, users, posts, likes, and things like that. Okay, and what do we usually use this data for? There are kind of two use cases for this data. I would say there is the descriptive use case, where we are asking kind of what has been happening with our business in the past, and we are building dashboards and metrics to track how the business is performing, how different clients, users, customers are behaving, and so on and so forth. But today I don't want to talk about kind of the left-hand side of the slide. What I really want to talk about today is the predictive part, where we are asking about kind of what is going to happen in the future, right? Kind of what can I forecast product sales for the next month, next quarter? Can I, forecast or predict which of my marketing sales leads are actually going to convert and, let's say, sign a contract next quarter? Can I model and predict which of my existing clients is going to churn in the next 365 days? Can I predict whether a given transaction that I'm just about to allow, is that transaction going to turn out fraudulent or not, right? So these are examples of predictive use cases on this type of data. So the first thing I want to talk to you about today is to kind of discuss how do we solve these problems today? How do data scientists build and solve predictive problems today? The way we do this is through this kind of, it takes many steps. It's very manual, and it takes a very long time, right? So we ideate the problem, we prepare the data, identify what data we may want to learn from. Then we spend a lot of time kind of feature engineering, creating features. Then relatively little time is actually spent on developing the model. And then once we are happy kind of with an offline model, we want to productionize it, and putting a model in production deployed is another kind of big step, because all the features we have engineered maybe in some notebook now have to be put in production. Features need to be backfilled. There might be issues with time leakage, information leakage, time travel, and that takes months or very long time to get there. So the point is that this process is very tedious and slow, taking many steps, many days for the data scientists to build this type of predictive models. And the key kind of problem in this process is the feature engineering, right? In a sense that we have here very nice relational data, nicely structured on the left, but we don't have, let's say, AI machine learning methods that could just learn over this data. Today, methods only know how to learn essentially from a single table. So what data scientists are spending time on is doing features, right? Basically taking this nice, in this case, 5-table schema and flattening it into a single table to try to create the training data set that then, the models can be trained or fine-tuned on. Right, and if you look at this here, I actually have an example where we hired a senior data scientist to. This is from a research project at Stanford University, where we took a data set from the RHEL Bench open source repository, a data set coming out of Amazon. And the task for the predictive model to build is, will a given Amazon customer, a given user, are they going to churn in the future? So basically they won't buy anything for the next K number of months, right? And here you have some ideas for the features that the data scientists wrote down. So he was like, okay, how old is the user? And let's quantify the age of the user by the number of weeks since the user wrote the first review. How many reviews have they written? What kind of ratings have they given? What's the sum of the review ratings? What's the average review rating? And so on and so forth. And you see some ideas for these features here. You start noticing that these features are kind of arbitrary, right? Like, for example, here I just say no number of reviews in the lifetime of a user. How about number of reviews in the last month? Maybe in the last 7 days. Why 7? Maybe we should choose 13. It's a lucky number or whatever, right? Here another one, you can see I'm saying, okay, what's the last review summary, right? Kind of let's embed that and say, okay, what was the review of that last? What was this kind of the summary of the last review? But why last review? How do we determine that, right? And so on and so forth. So kind of what I'm trying to say here is, you see how kind of arbitrary these features are, right? I have this beautiful relational data here on the left, and then I choose, or as a data scientist, to kind of summarize it with this set of features. And if you don't like these, you can add more to them, but there's always an opportunity to add even more and more and more. And if you'd like to kind of do more and learn more about this, then here's a GitHub link to the study. So and then right now that I ideated the features, then I have to program them. So I have to write, let's say, Spark jobs or SQL statements that actually go join the tables, aggregate the tables, and compute these features. One problem here that is quite important is this notion of time travel, right? Because the events are happening over time. I need to keep my features up to date. So it means that kind of whenever a new event arrives, I need to update the features. I need to recompute them because, you know, the sum of the review scores might change. The number of reviews the user has written might change. The average rating that the user has given might change because, you know, one more review has come in. And of course, if I do this for every event, that's very costly. Now, if I only do it on some cadence, then my features will be stale, right? I update the feature by the 1st of the month, but I want to, you know, use the model on the 20th. So I lost 20 days. And another problem with this approach is that many times, kind of due to human error, we compute a feature from the feature from the future, and then the problem is that we have time travel, information leakage, and so on. So, you know, what's the bottom line? What I'm trying to say, right? Kind of, we did not become data scientists to basically work for months to do this endless feature engineering that is kind of never done, and then, you know, build a model that's kind of an okay type of a model. And then the second thing that this kind of, because this process is so manual, another consequence is that we have these very brittle pipelines that we have to manage, right? That basically and usually the entire process is done in a notebook, but you cannot put a notebook into production. You have to productionize features because they have to be updated. You have to make sure they are computed in the same way than what you computed in the notebook. There might be discrepancies there. That means either your model is kind of going to, you will think that it performs really well, but it won't, or the other way around, and so on. And then, right, once you've done all that, then you have this kind of very brittle, basically system stitched together that is very, very hard to manage, lots of on-call hours, lots of failures, very expensive to run computationally, and so on. So kind of my point is that, you know, this is kind of the boring part of the data science. What's the exciting part of the data science? The exciting part is to architect models, to train and improve models, find new areas of the business where AI, machine learning can be applied, and come up with actionable predictions that actually can impact the business, that make the difference to the business and create new value to the business, to the organization we are working on, right? That's the exciting part. So, you know, the question is, how do we change the status quo? So this is really kind of the research question we asked in my research group at Stanford AI lab a few years back, and said, okay, how do we change this? Does this have to be, you know, so manual, so kind of human involved, so brittle, and also like something, it's like almost like suffering, right? Does it have to be suffering? Shouldn't the life be happy and good and exciting? So this was also just the time when kind of transformers and the transformer revolution was happening, right? And you know, one way to understand transformers, which revolutionized the natural language understanding, is that kind of transformers just kind of learn on the raw textual data, and they kind of capture the meaning of textual data. So, you know, with my students, we asked, okay, can we design AI algorithms that can kind of capture the meaning of relational data? And that would be huge, right? Because the majority of useful business data is relational. So could we kind of design AI methods, algorithms that capture the meaning of relational data? So we came up with the approach. We published a paper at ICML in the summer, and we are actually presenting another research paper at NeurIPS today or tomorrow, because NeurIPS is going on in Vancouver, kind of as I speak. And we came up with this very exciting technique that we call relational deep learning, or, you know, relational AI. And what I'm going to talk to you today and teach you today is how does this work? What's the idea? And what difference does it make? So there are two key insights in this field of relational deep learning. The first key insight is that all predictive tasks can be described by a very simple domain-specific language. And then the second insight is that all predictive tasks on structured data, meaning on a collection of tables, can be learned by basically representing the data as a graph and then applying a graph transformer or a graph neural network on top of the data. And if you kind of put 1 and 2 together, you get a much more efficient, much more nice to use, and also much more performant AI platform, where the data preparation is kind of minimal. There is no feature engineering. There's no need to babysit ETL pipelines, and putting a model into production just means to refresh your raw data, and the rest is being taken care of. So it's kind of truly revolutionary. And that's kind of what we believed when we set off on this journey. We said, look, if this is what is going to happen, then it's worth our time. Let's go and do it. And that's why kind of we are so excited about it today even more. So what's the first insight? The first insight is that if you want to build, let's say, machine learning AI models, what you have to have is a training table, right? And a training table has a very kind of simple structure usually, right? There is the entity, let's say the user ID for the user we are making a prediction for. Usually we are making, let's say, that prediction at a given point in time. So there is also time associated with the time of that prediction. And then we know the label, what we should be, what is the correct answer, right? So the label can be a true, false, kind of binary. A label can be a real number. So, regression in this case, we could have a set of labels as a label, and then it's a multi-label classification, multi-class classification. It could be a set of other entities, and then you would call it a link prediction. So a recommendation is an example of this, where for a given user ID, the label would be a set of products that the user purchased at a given point in time, looking 2 weeks, 3 weeks into the future. In forecasting, the label is a time series of future values, right? So the key is there is kind of this training table with the entity for which we are making the prediction, which is usually, a customer, a transaction, or whatever that is, has a very kind of like clear structure. So the point is that if this is what kind of defines machine learning problems, there is actually a very small set of operators that allows us to define predictive tasks, basically allow us to specify the training table. So we have developed this domain-specific language that has a structure of a predict part for each part and a where part. And in the predict part, we specify what is the target we want to be predicting. So for example, for this simple schema here on the left, the target would be predict whether the sum of transactions dot price, right? Because every transaction has a price, between now and 30 days in the future, tell me basically what is the sum of transaction prices. Now, who are we predicting these transaction prices for? We are predicting them for every customer ID, right? For each. And then, for example, here I could say, okay, and let's only make this prediction for the customers where the count of transactions in the 30 days before now was greater than 0. So basically, I'm saying for every active user, predict me how much they're going to spend in the next 30 days. And 3 lines to specify this predictive problem. If I want to, for example, do product sales forecasting, I could say, okay, some transactions dot price, let's say 3 months into the future, but now for every product ID, right? I don't, I can use a sum operator, I can use a count operator, I can use a least distinct operator, and I can say predict least distinct, transactions dot product ID, 7 days into the future, give me top 10 for every customer. And this is a recommender system because I'm predicting what item IDs a customer is going to buy. Why is this predictive query, this DSL important? Because we can automatically interpret it and basically slide through the data and automatically generate the training table. So there is no need for a data scientist to manually generate the training table. The training table is fully specified by this predictive query. Now that basically we have the training table, now we just need to learn the model. So how do we learn a model without doing any feature engineering? The way we learn the model without feature engineering is to realize that any database is a graph. And the way we talk about this, we call it's a graph of data. It's a graph of entities that are related with primary foreign key relations. So we can take a database and basically through a one-to-one mapping build what we call a relational entity graph, which is a heterogeneous temporal graph that is based where the relations are based on the data in the relational tables. So each table defines a node type. Each row in a table is a node. So every customer in the customers table is a node, every transaction in the transactions table is a node, and every product in the product table is a node, right? But transactions points to a customer and points to a product. So this now defines our links, or our kind of hyperlinks, hyper edges. Columns that in these tables, like whether the customer is active, what is their age, what is their postal code, are properties associated with the node, right? So a product can have a product name, product description, product image, all those can be attached to the node as well. So now that I have a graphical representation of my data, I can also take my training table and just kind of attach it to my graph, right? So now if we have our churn example, for every user, I have a label, and this label is at a given point in time, right? So this first user here, maybe in May, they churn because they didn't buy anything in May, but in June, they become active because they bought something in July, right? So the label can be different through time. And now everything is nicely put together. So now that everything is put together, we can actually apply methods like graph transformers or graph neural networks to learn from this richly labeled relational structure. And the key insight here is that we can basically take the attention mechanism and generalize it so that the attention mechanism can attend from the user's table to the transactions table, from the user's table to the stores table, from the user's table to the products table, and this way learn a representation that is, predictive of the downstream task, that allows us to predict the downstream task, and we can train this kind of with standard backpropagation automatically. And the exciting thing here is that now basically we have a neural network that can learn a model directly on the raw data. I don't need to do any feature engineering, right? It just learned directly on the raw database. And that's the exciting part. So the interesting thing here is that this framework supports like the full universe kind of predictive tasks. We can talk about kind of node prediction level tasks, which would be kind of classification, like classification of users, segmentation, next best action, churn, lifetime value, as well as regression. We can think about link level tasks where we can be classifying links like product affinity recommendations. We can be doing fraud detection, link regression and things like that. So a lot of different tasks can be naturally expressed in this relational structure. And why are we so excited about this? The reason we are excited about this is because kind of data science and machine learning are stuck in the past, right? They are stuck in this manual feature engineering world. And this is exactly where, let's say, computer vision used to be. In the old days, you would take an image and you would do your feature detection. You would use Gabor filters, sift features, or whatever, and then you'd build a classifier to say what is in the image. Today, in computer vision, nobody's doing that. Today, in computer vision, you have a neural network that learns directly on your raw data. It learns directly on your raw pixels, and you get superhuman performance. So it was a step function change. Now, with the relational deep learning approach, you basically get the same benefit that computer vision got when they went from manual feature engineering to neural networks. Now, kind of as a data scientist, you get the same benefit. Kind of for the first time, we have a neural network that can just learn over your raw relational data. And, when do you use the approach as I talk about? As soon as you have data in more than one table. If your data naturally comes in one table, then yes, use XGBoost, use neural networks, use whatever you want to use, right? MLPs, whatever it is. But if your data comes in multiple tables, then relational deep learning is actually the only technology that allows you just learn across those multiple tables. Why is this interesting? This is interesting because it shifts the effort from manual feature engineering to better model building, gives the neural network a multi-hop reasoning ability across table boundaries that can kind of catch information which is hard to pre-compute or kind of hard to come up with beforehand manually. And what is very interesting in this approach is that it learns both from the properties, features of these objects, but also kind of uses the relational information, the kind of collaborative filtering signal across different examples, right? And that's very exciting and leads, for example, to really good performance in recommender systems. What I want to do next is quickly tell you more how this is working, right? Like basically the way we can think of these neural networks is that they are going through three steps. In the first step, where basically we encode and transform these individual entities, properties, features. Then we kind of correlate them through the sparse cross-attention mechanism to basically between facts, so that the network can learn patterns like bought together, repeated purchases, trends, differences in time between events, and things like that. And then the last step in this neural network architecture is to do this kind of multi-aggregation operators that basically imitate this kind of group by that you do in SQL. But here you are using attention mechanism where you can learn weights, how to add these embeddings together, count them, sum them, and understand them at a much finer grain. And all this is parameterized and learned through backpropagation. Nothing here is manual. What does this mean? Is that now you have a super flexible neural network that can learn over your relational data to give you a model that is tuned for a specific task that you specified in 3-4 lines of the DSL I showed. So we actually did a user study, and I want to show you kind of the difference between a data scientist equipped with a database to be able to compute features versus being equipped with an RDL. So here we hired a high-end data scientist, somebody with a 4.0 master's degree from Stanford and 5 years of industry experience, specializing in building models in financial industry. And they were responsible for the full model building lifecycle. So we took, in this case, a data set coming from Stack Exchange. It is, these 7 tables. It's about posts and badges and comments and users and things like that. And the predictive task is, predict whether a user will be still active 6 months into the future, right? It will between now and 6 months in the future, user write any posts. So how did this go? So the data scientists actually spent one day just doing data analysis, familiarizing themselves with the data, plotting the data, figuring out, activity, seasonal number of comments per user follows a power law, how positive and negative votes relate, and things like that, right? Kind of familiarize themselves with the data. Then the person sat down and for 1 hour were just writing down ideas for features. And then, for the rest of the day and into the evening, they were coding features. I think they need to write about 1,000 lines of code to generate these features. And then after they had all that, they were so tired that they only spent about half an hour building the model with XGBoost and so on, and did some analysis of feature importance to get some ideas what to do next. And what they noticed is that from all the features they generated, only a few were actually really important, right? But they learned interesting things about time since last activities, predictive, and so on, and which are predictive and which ones are not. But you can see that very few of the generated ones are predictive, right? And then you would iterate, right? And try to build a better model. So in the end, the person coded up 54 features, took 30 hours of high quality expert work and about 500 lines of code in Jupyter. So what were the results? The results were that, for example, if you would just take the users table and from, kind of users properties, try to predict whether they will be active on the site, your AUC, the area under the receiver operating curve, is about 6.8. after all this process of 30 hours of feature engineering, you get better model. You're about at 86%. So it's 30 hours of manual work plus 5 hours of GPU to train the model. So about 4 days, 5 days of work, right? Really focusing on this. If you are using RDL, it takes you 54 lines of code, 50 GPU hours, so a bit more compute to get essentially the same or let's say slightly better model. Right, and the point here is not so much that the model is better, as much is the point that here it took about 10 times less work, less code to write. So how did it compare? With RDL, the person was able to do this job in less than an hour versus 30 hours of the steps I showed. They needed to write about 50 lines of code. They went to sleep so that overnight the compute could happen, and they got, in the end, a 5% more accurate model. So we've tried this, replicated this over a lot of different predictive tasks. Here I'm showing in terms of performance, and we see that the expert data scientist and the RDL kind of match, and sometimes RDL actually outperforms the data scientist. But the huge difference is in the time needed to build the model, in number of hours of human labor. And we find out that the number of human labor goes from 12 hours in feature engineering to about half an hour using RDL. And if we also do it by the number of lines of code, we see a 94% drop, so about 20x on average less number of lines of code. So this is what I wanted to show you about relational deep learning, how it works, what benefits it gives you, and how it compares in this setting where the data is already clean, the data is already there to be modeled, and somebody essentially spending 1 week to tweak to build a model, to build the features and so on, versus the deep neural network training over the raw data, giving better performance in a fraction of time. And what we are going to do next is Ben here is going to show you how easy it is to achieve what I showed you in Kumo, which is a production-ready, super scalable platform to be able to build predictive models directly on your raw multi-tabular relational data. Ben, you can take it away.
Great. Thank you so much, Jure. I'm going to share my screen here real quick. Okay. Hopefully everyone can see my screen now. I will reintroduce myself briefly. My name is Ben Berger. I'm a data scientist at Kumo. And so as Jure mentioned, the last thing that we're going to kind of walk you through here is we're going to, I took one of the RelBench use cases that Jure mentioned a couple times in his presentation, the customer churn on that Amazon e-commerce data set use case. And I'm going to go through the process from scratch of building a model via relational deep learning in the Kumo platform. So of course, Jure just talked to us for the last 30 minutes or so about the amazing efficiency and performance gains that you can get from relational deep learning. And Kumo is a platform that's meant to empower machine learning practitioners to build machine learning models with relational deep learning in a streamlined way and at industry scale. And Kumo is a platform that can handle billions of rows of data, 30 billion edges. So it's meant to be developed and executed at a production scale. So I'm going to show you what the workflow looks like in Kumo to build this model. In the SDK, there is a UI that I'll flash in a little while, but in the spirit of comparing lines of code, we figured we'd show it to you in the SDK. So to kind of start off to initialize the SDK is very simple. This is the Python SDK. It's pip installable, very easy to import and get started with. And all you have to do is sort of initialize the connection to the actual Kumo platform with a provisioned API key, and you're on your way. So very high level, the first part of the the Kumo workflow is sort of this data specification process, which is hopefully pretty intuitive and pretty simple to give you the foundation to lay predictive tasks over and to train models. And it's pretty much 3 steps. You define the connection between the Kumo platform and your raw data source, so in the connector here. Then you define the tables that you want to be ingested in for modeling purposes into the platform, and how the platform should ingest those tables. And then finally, you instruct the platform on how to materialize the graph given those relational tables when it comes time to train the GNN over it. So let's get started. So the first step there is connecting data. It's a very, very simple step in the Kumo process. Kumo integrates very easily with data warehouses, so Snowflake, Databricks, BigQuery, stuff like that. For this use case in this schema, the data is sitting in Parquet files in an S3 bucket. So I make this S3 connector here, give it the location of the bucket, and now I've established that connection between Kumo and my raw data sources. So now that I have this connector object, I can check with a couple of these methods to make sure that the schema that I believe is there, that all the data that I want to be there is actually readable by the platform. This is a very simple e-commerce schema, just customers, products, and reviews, so we're all good. And before you kind of jump into any of the more Kumo specific stuff, you can use this object and index into the tables and retrieve samples of the raw data itself. To get familiar with the tables, with the columns and everything like that you probably go through in your typical exploration data science process. So now we're ready to move forward to the next step of this data specification phase, which is creating tables. So it's really giving the Kumo platform the instructions on which data to ingest into the platform and how exactly to read it in. And that really kind of takes 3 basic things for each of the tables that you want to read in. You have to flag or determine any primary keys that exist in each of the tables that you want to include. Determine or flag any time columns if there's a temporal aspect to what you want to be modeling. And then most importantly is confirming the raw data types of each of the columns in each of the tables that you want, but also the semantic types or the Kumo types. So essentially how Kumo will encode and interpret those features when it comes time to model. So from the platform and in the SDK, this is as simple as for each of those tables that are available in the schema, to define this Kumo table object, we simply pass it. This is the connector object pointing to where the raw data lives. Determining whether or not there's a primary key or there's any time columns, and then for each column that you want to include in that table, determining those raw data types and those Kumo data types. So a couple of those S types you're probably very familiar with: categorical, numerical, very classic types of encodings that you go through in your development process. But the platform is also capable of reading and ingesting freeform text fields. So a language model behind the scenes would encode these raw text fields and use them for modeling. You can bring your own embeddings. The platform can ingest and leverage embeddings that you bring as well. There can be multi-categorical fields. So there's a lot of flexibility in what type of data the platform can ingest and leverage. So as we kind of touched on before, there's 3 tables in this schema: products, customers, and reviews, and we just create these Kumo table objects for each of them. So now we can move forward to sort of the last step. We've done the connector, we've done the tables, and now we're at this last step of the data specification process, which is creating a graph object. And as Jure mentioned a couple times in his presentation, relational deep learning in Kumo is predicated on the idea that your relational data is a graph, and all you have to do is specify which tables you want to be included, and then confirm what the primary and foreign key relationships are between them. So in the SDK here, that's as simple as just creating this graph object, passing each of the 3 tables that those Kumo tables that we just created, and then confirming what the primary key and foreign key relationships are between each of those tables. And as Jure mentioned, to reiterate, every row in each of those tables would be a node in the graph, and the existence of any edges between them would be whether or not there's a primary key, foreign key relationship to another node in a different table. So we've kind of finished the data specification part of the process here now. We're left with this graph object that will be the foundation for laying the predictive tasks over now. So this graph object includes all the instructions on which tables to read and how to connect them. So now we're kind of moving more into the modeling part of the workflow in Kumo. So now that we have sort of this base graph object that we've worked to create in the last few steps, we need to define the predictive task that we want to operate, the model that we want to train on top of this graph. Jure mentioned it briefly in a couple of the slides in his presentation, but a whole universe of supervised machine learning tasks can be described with a very simple set of operators. It ought to be articulated in a very simple syntax. So Kumo leverages its own predictive query language, PQL, which is meant to be the SQL-like syntax to define these predictive tasks. So as a bit of a reminder, the actual task from RelBench, so the actual use case that we're going to do here, is customer churn prediction. So the actual task is predicting if the customer will not buy any products in the next 2 years. And so this entity filtering part here is we only want to provide these predictions for active customers, so customers that have purchased or have written a review in the past 2 years. In this schema, the review table is just a proxy for purchases or transactions. So to translate that into this predictive query language, as Jure briefly went through earlier, the for each clause here defines the entities that we're predicting on, so in this case, the customers, and the predict clause here would define what the actual label is. So for each customer ID, predicting whether the number of records, the count of records in the reviews table for that customer ID over the next 720 days is equal to 0. So that's a way to frame this churn problem and translate this task definition into the predictive query language. And we also do have the ability to do this entity filtering, so only for customer IDs that have a review in the prior 720 days. So all of the ways to articulate these machine learning tasks you can do with predictive query language. So at this point, at least to bring it back to the code a little bit, we've created this predictive query object. We've passed the graph, which is the foundation that we work to build, and then we've applied the query, which is the definition of the predictive task over the graph. So this pQuery churn object is now going to be the foundation for a lot of the stuff that we do afterwards. So now we can kind of get into the process of actually triggering jobs. This process can be coupled together. I've decoupled it for the sake of demonstration. But the first thing that you want to do, Jure mentioned briefly in his slides that this predictive query that we've written and combined with the graph are as much information pretty much as you need to generate the training table for the model to learn on. So the first job that we would want to send to the platform is to generate a training table. Before we can do that, there are to trigger that job does require this training table plan. So these are a few configurable parameters to determine your train test val splits, stuff like that, all configurable and flexible within the product. But we have our pQuery object here. We can actually ask the platform to suggest, given that pQuery, to suggest a training table plan. And for simplicity's sake, I will just use the one that the platform has generated. And now we're actually ready to go and trigger the job to create the training table. So we take our pQuery object, we call the method to generate the training table, we pass it the table plan that we just created, and this will have triggered a job in the Kumo platform to create this. So I've done all this ahead of time. It's completed. So once that job would be completed, you could grab the job ID, you could read the result of the job back in, and for training table generation jobs, you could explore the actual table that was created, get familiar with everything, stuff like that. So there's always the ability to interact with the results of all these jobs. But assuming we were comfortable moving forward, so now we have our pQuery object, and we have a job that has created a training table, so we know that it exists. We can actually move forward to triggering a model training job. And again, similar to what we did with the training table plan, before we can trigger this job to model training jobs also do need model plans. So in the model plan, this is where you could configure very familiar things like hyperparameters to tune all part of your traditional development lifecycle, very graph-specific type of parameters to experiment with, everything like that, overriding any of column encoders. All that stuff is available to configure in the model plan. And again, for simplicity's sake, I'm just going to ask the platform to suggest that model plan for me. And then when we go down here to actually trigger the training job, we will pass the plan that we created. So actually,
Ben.
Yeah.
Yeah, I will just maybe add one thing about this is, so when we were designing kind of the product and the platform, we really wanted to cater to a large audience of data scientists, from kind of citizen data scientists all the way to, super expert, high-end data scientists, machine learning engineers, and so on. And one way to do this is through this model plan, where the platform, our platform analyzes the data and says, this is what I propose, how I propose to go about this problem. I propose to tune the AUROC metric. I propose to do this kind of data sampling, this kind of learning rate, all that. And the defaults are already good, but if you're like, I want to squeeze out the last percent of performance out of this model, you can kind of start playing with this knob the way as we all do, and really find the best model. So this is just a way to give you full control when you need it, when you want it.
Absolutely. Thank you, Jure. Yeah, none of these details that you would typically want to tune are abstracted away from you in the platform or in the SDK here. So again, if we were happy with this model plan, we could move forward to actually triggering the job in the platform. That's as easy as defining this trainer object, passing it the model plan that we just created, and then probably very familiar to many of you, just calling a .fit method, repassing that graph that we've created, and the training table job so that those are connected. And now this would trigger a model to train in the Kumo platform. So again, I've done this all ahead of time. So once the training job were to be completed, you could read it back in and get, this is a binary classification problem. So you could read the results of the training job back in and explore a lot of the metrics, explore the holdout set, to get comfortable or to try to understand how the model performed. But if you were like me, you probably would prefer to visualize most of this stuff in order to get comfortable with the outcome or a model that you've trained. So I'm going to jump into the UI here, and this is the job ID of the training job that we had created. And this allows you in the UI to actually explore the results of the training job in a much more visual, and for me, a preferable way. So you can see the experiments that the training job ran. So this actually trained 2 different models, and the performance of each of those experiments in training and validation. You can also see on the test set, this is a binary classification problem. So all of the classic metrics that you would want to use to evaluate model performance on the holdout set are available out of the box in the UI here. Your ROC and PRC curves, the confusion matrices, everything you would want to get comfortable with model results are available here. And then the last thing I'll show is the explainability that exists here in the UI as well. So this would be at the entity level of the holdout set. You can explore the predictions that were made at a very granular level. So the entity level is a customer here, and you could see the subgraph for that customer. So essentially the information that was aggregated and sort of implicitly creating those features like Jure talked about earlier, what information was being aggregated to that entity and how were the predictions created. And then at a little bit more of a granular level, you can see sort of this, I guess, quasi-feature level importance or contributions to each prediction. And some of those are aggregations. So we know that these GNNs are aggregating information across a number of different neighboring nodes. It can also be at the feature level, depending on the data. So all that explainability comes also out of the box in the UI here. And for me, much more preferable to explore this in a visual way than it is in the SDK. And then the last thing I'll do before I wrap this up is just mention that if you were to get comfortable and be happy with the model that you've trained here, all of the artifacts that are associated with that training job are persisting. So you can build a pipeline in the SDK or outside of it to call those artifacts and create production pipelines to bring these models into testing and actually have this be a 0 to 1 platform. This will bring you from nothing to production to these models very quickly. And yeah, so that's in its most basic form, kind of the workflow of Kumo and how you would tackle one of these predictive problems. So I'll stop there and I guess hand it over to Ketty.
Thank you so much, Ben, and thank you, Jure. Now we're moving on to the Q&A. We received some excellent questions and we will be addressing them. We will dedicate maybe 20 minutes to be able to answer as many questions as we can. So I will read the first question, Jure and Ben. The first question is there a mechanism to use natural language to create the DSL output? This would help any business person easily use this amazing work.
Yeah, that's a great suggestion. We actually have a prototype of this feature. It's very easy to build. But maybe the point here is that as a data scientist, you really need your data. And you know your columns, you know your tables, we wanted to give the full control and full flexibility to the data scientists. And since data scientists are familiar with SQL and things like that, then kind of learning another kind of dialect of SQL is not too hard. But for example, what we can allow is that you kind of pre-select, let's say, the data you want to be using. But now if people want to have customizable predictions for different types, definitely those could be specified in the natural language.
Thank you, Jure. The second question is, do you need to do anything special for it to learn the time component? What if the transaction are the timestamp level and the churn status is a week or month label? Do you collapse all 2 months?
This is an excellent question. So in Kumo, time is a first-class citizen. So we truly take kind of consider the time. We don't collapse it, and you as a user, as a data scientist, you specify this is the reference time. This is the time point. This is the time column. We have the start time. We have the end time. So we can understand in their kind of events that kind of come and go. And then when we learn, we use these timestamps to make sure we only learn from the past. We never go into the future because things are timestamped. So when we look at a piece of information, we say, oh, right now the reference time is X. Does that piece of information come before that X or not? If it comes before the X, we can learn from it. If it does not, we have to omit it. And this way, our models don't have any issue with time travel. Information leakage may still happen because you might have kind of a column that just duplicates the label somehow, but through the explainability you discover those super quickly. So we don't see like this kind of super hard to resolve bugs in Kumo because time is a first-class citizen. Thanks for asking the question.
Great. Next question. Sometimes when we ETL a database to a graph to optimize storage, some properties are decoupled into relationships or additional nodes. Can these predictable models take care of the properties in relationship too?
This is another, I think, very insightful and good question, is because Kumo will learn from the schema that you define. But many times there are many different ways kind of to define the schema, to decide the tables, to decide the relationships. So we see it as a part of the data modeling process, as a part of creating the graph that Ben showed, to kind of organize and think about the relationships between different entities, bringing in tables and telling the platform how those tables are connected. So I would say, the modeling is over the tables and over the columns that you define. And you can then play with the relational structure of those tables, which tables, what columns to use. So, and that's usually the first thing where the data scientist iterates is about what data am I learning over, what events, what tables do I bring in, how do I connect them into a relational structure.
Thank you. What happens if we have multiplied tables, not just products, user, transaction? What if there is an onboarding funnel table and 2 different transaction tables along with the table shared in the example?
Unless I'm kind of missing something, there is no problem. You could. The approach, as I explained it, supports any kind of schema, any kind of arrangement for any kind of tables. I think with Kumo, we trained with a client, basically one of the largest insurances in US. I think they had 30 tables in total, if I remember. And I think the product internally, we tested it with up to 50 different tables. So we were able to build a model over 30 tables, no problem. And you can just imagine how hard it is to do manual feature engineering over a schema of 30 tables. It's a daunting task. With Kumo, the client didn't need to do any of that. So it is not a problem at all. You can learn over tens of tables models very easily.
Next question. How can we handle a high number of columns while having only relatively low number of rows? So how to handle overfitting best? One example would be biological data having large amounts of genomic and proteomics information while having only low sample numbers due to expensive laboratory experiments.
Thank you for the question. The reason I'm laughing is because these questions are so good that I'm like thinking, has somebody paid or people to ask exactly the right question? So I'm really happy because this means people really understood. This is a great question. So technically, I think Kumo supports up to 2,000 columns in a table, not kind of the biology's dimensionality, which is I don't know, usually like 20,000 plus or something, right? But a few thousand columns. What is nice about this approach is that you can basically, if you have data that is kind of very wide but shallow, that you can kind of specify the capacity of your model, and through the capacity of the model, you can basically trade off between the width and the depth of your data. And this is very nice because for some clients, for example, we are training models on tens of billions of transactions over billions of entities. For example, for detecting fraud on the blockchain network. And there you have a big model because you have enough data to support a big model. But in some other cases where maybe the amount of data is smaller, like the number of rows is smaller, but they are more, but the data is wider, there you want to kind of come in with more inductive bias, with more biased model, so that it can learn in a generalizable way and doesn't overfit. Another option would be in these kind of places would be to maybe use a foundation model to encode your high dimensional biological data, right? So if you have, I don't know, single cell RNA-seq data or something, you would use a kind of a cellular foundation model. Or if you have something different, and then use those embeddings that are now much lower dimensional as inputs into Kumo for your predictive models. Thanks. It was a good question. Yeah.
So we have two questions in one. What is the additional overhead of converting the relational data into graph data structure? And the second one, since the resulting graph is heterogeneous graph, how would you take care of the node attributes in GNN, which I presume would be the starting node representation?
Good questions. So, I mean, in terms of overhead, I'm not sure kind of what do you mean. What do you mean by the overhead, right? There are, so basically from the tables we create a graph. The simplest way to create the graph is to have every row is a node, and then primary foreign key are relationships between those nodes. But if you kind of naively generate those graphs, they will become very wide, and the information flow through them will be challenging. So there is a lot of kind of optimizations you can do to kind of automatically build better graphs. When I say you can do, Kumo does, maybe that's the way to say it. And then, so the graph is built. Then to be able to now compute over the graph, Kumo had to build a very fast kind of graph engine that stores these graphs and supports mini batch sampling. So there went a lot of time and energy into building that kind of AI focused, graph engine. And then you bring in, now that you have the graph, you bring in the attributes, and the attributes are the columns. So every node, every row, the columns of that row, those are the attributes of the node. And the GNN, or the graph transformer, is learning from both. Is learning from the relationships as well as from those properties. And when Ben was saying about when we define a table, we define the D types and S types. The reason we do that is because we basically say, how do we want that those attributes to be encoded, right? If it's a string, do we want to encode it as a text, or is, you know, a string really just a name of the color? So it's red, green, blue, and that's a categorical encoding. And you as a data scientist kind of select how that data gets encoded. And then, you know, let's say in your case, you mentioned GNN, the GNN then learns how to kind of aggregate and transform this information across the graph to be able to predict the label, to basically solve the predictive problem you specify in the predictive query language. I hope this kind of clarifies the steps of what is happening.
Thank you. As I mentioned earlier, we will dedicate 10+ minutes to answer the question. So the next question is, how does the proposed method perform in case of limited training data?
Good question. So we see the following, right? Like, as I was kind of answering this a bit earlier, right? The approach is so flexible that it can train with a few hundred training examples all the way to tens of billions. And when you have a smaller number of training examples, you basically choose kind of smaller models. You're also more careful about how the data sampling is done, which you can kind of further control through the model plan. So the models that can be built with relational deep learning, you know, can vastly vary in size, from small models that require small amounts of data and smaller amounts of labels. As I said, the smallest number of labels we saw when working with clients on use cases was a few hundred. It was like, I think 300, 500, something like that. And the largest was in tens of billions. And kind of the platform was flexible enough, or is flexible enough to cover this range, even though there is kind of multiple orders of magnitude there. Yeah, thanks for the good question.
So we received a few questions, and the question is, people are asking if we'll share the notebook and how they can replicate this. So Ben, maybe you can help me with answering this question.
Yeah, sure. So I think if the curiosities come from just looking at the code and seeing the workflow and how the SDK works, I'm sure we'll be able to circulate the notebook, or at least a version of the notebook afterwards. As far as getting an API key and access to an actual environment, we're in the process at Kumo of making or giving sort of a preview or self-serve access to this. So that might come a little bit later. But if it's out of curiosity, sort of about the flow and the SDK itself, we can circulate some version of it. Yeah.
Just send us email. There is a forum to register, and we'll be in touch after the webinar to kind of open this up to more users.
Yes, I will also share your emails and also our website link if someone wants to request a demo or get in touch with you. Great, thank you. We have one specific question for Jure. How would one justify using GNNs for, say, generating user cross-item embeddings via decoder LLMs to the same thing?
Sorry, I don't see the question.
Yes.
I saw the limited training data. I saw.
Share it in our Slack channel.
Sorry, I can't. Can you maybe choose the other question and let's return to this one?
Yes. The next question is, how can I integrate this automated feature engineering with Databricks? I'm interested in fraud detection, where I have to manually calculate graph-related features, like the number of cards used by the customer in the last 30 days.
There are two answers to your question. So with Kumo, you don't have to compute any of those features because the neural network can learn the same pattern, the same signal, if it turns out to be predictive of your problem. So the second part is you would just apply Kumo. If these are, kind of amazing type of signals patterns in your data, the neural network will kind of spot them, model them in its own way, and you'll get a really good model. And the second thing is, since you mentioned Databricks, we have a very, very good integration with Databricks, where basically there is just a Databricks connector. You point Kumo to your Databricks table, and everything works beautifully. So you could very easily integrate this with Databricks. And the beautiful thing is that basically the Kumo does not store your data. Kumo just kind of connects to your data source. So the data is stored in Databricks. Kumo will then train a model. And now to put that model in production, you just point Kumo to the fresh data, and the Kumo neural network is going to kind of read that fresh data and give you predictions. And then predictions are again written back to your data warehouse as a new table. And then you can consume this table however you like. Kumo can also output embeddings so that you could, let's say, get an embedding for every transaction and do something with that embedding later if this is what you wish to do. So you can get both embeddings as well as predictions. Next question.
Next question, what options, if any, are built into Kumo AI for post hoc interruptions of features if we actually care about understanding feature importance?
That's a very good question. So there are no features in Kumo, right? Kumo is a neural network. There's no features. No features get engineered. So that's one part of the answer. So what this means is that actually at Kumo, we have to totally rethink what this explainability, interpretability really means. And I'd argue that our explainability, interpretability capabilities are even better than what is out there today, because classical approaches just explain your predictions with the features that somebody happened to engineer. Kumo gives you explanations that that you can trace kind of all the way down to the raw data. So Kumo kind of points back to the raw data and says, I use this data, I use this evidence to make this prediction. So you can ask it, what was the data that gave you the most confidence in this prediction? And this way you can get very deep insights very quickly, kind of what the model is looking at. So, to answer your question differently, the way we think of explainability in Kumo is similar kind of in computer vision, where you can ask the neural network that's maybe classifying humans, you ask it, what are you looking at? And if the neural network is looking, I don't know, at the eyes, at the nose, at the head, you say, oh, you are looking at the human to classify human life is good. If the neural network says, I'm looking where there's, light above someone's head, then the neural network is kind of picking up spurious patterns. So that's kind of our explainability capability.
Thank you. Next question. What about latency in the deployed model? How long does it take to respond?
Another good question. So usually, let's say maybe I'll expand your question a bit. So in terms of training Kumo models can take from 20 minutes on a few millions of rows to maybe a day, 2 days if you have tens, hundreds of billions of rows. You have, I know, close to 1 billion users. You're a social media platform where people write, I know, 140 character long messages. Then if you have that amount of data, then it takes a day or two to train a model. But if you're smaller, it's much faster. Now, in terms of putting things in production, Kumo mainly supports batch workloads, where you basically orchestrate how often do you want to refresh your predictions, every day, every hour, every 10 minutes. And then Kumo is going to materialize that predictions. Those jobs, for example, we are doing restaurant recommendations for the largest food delivery business in US for all their users. Recommend restaurants people may order food from. I think it takes about 4 hours to materialize recommendations for, I don't know, 200 plus million users. So those are kind of the roughly the times to give you a sense.
Okay, and we will answer one more question. And the question is the following. Does the connector work with the local database with JDBC string, or does it require cloud solution Snowflake, like Snowflake that you mentioned?
That's a good question. Right now, we connect mostly to analytical databases because of the size and the scale of the data. So, for example, if you have some local database, you could just export that to CSV or to Parquet, and then, for example, Kumo can easily load that in. Can I answer one question that I find interesting, Katie?
Yes, please.
So I'd like to answer this question because, here the question people say, how does this compare to AutoML frameworks, that are out there? And this is fundamentally different because AutoML kind of came, I would say, with very similar promise, right? Kind of no feature engineering. But AutoML, the way they did that was basically to say, look, the way we eliminate feature engineering is that we are just going to blindly join tables together, compute all kinds of features, hopefully all possible features that are out there, and then we are going to train a gazillion of different machine learning models on those tables, on those features, and hopefully one of them will work, right? That's kind of, I would say what the kind of what that AutoML kind of approach turned out to be. And that's not scalable. It's not principled. It's kind of a humongous random search where you hope to get lucky. Kumo is different. Kumo is a deep neural network. It's a transformer architecture. It's a graph neural network that gets trained, tuned on the task for you, and it's the neurons of the network that kind of learn the representation rather than brute force generate it all and then throw it against the wall and hope that you got lucky. So in terms of both performance as well as scale, Kumo scales much more because it's so much more efficient and kind of it's kind of comes from the present day, because it doesn't come from history. Yeah, thanks for the question. That's a good one.
Thank you, Jure. So we have more than 50 questions that are pending. We will follow up individually after the event. And if you have any specific question, you can contact us at hello Kumo AI. Thank you all for joining. I hope you gain valuable insights into predictive modeling without feature engineering. To request demo, please visit our website or reach out to Jure or to Ben. We will send you I think that we have already sent our emails in the chat. Additionally, we are planning another workshop this month and we will keep you posted. Thank you once again for your time and attention, and have a great day.
Thank you so much, and thanks for great questions. Bye-bye.
Thank you very much.